Now, to understand the second law of thermodynamics, you must take cognizance of two thermodynamic concepts. One is the enthalpy, H. In the previous video, I made you to understand that the enthalpy of a system is the total energy package that system has. Now, think of enthalpy like an arranged pile of cards. The energy of this pile of cards is highly organized and ready to be used. Number two thermodynamic concept is entropy. Think of entropy like shuffling that pile of cards. And when you shuffle it, you will see that the energy becomes dispersed, spread out, and less organized. This spread out energy is what is called entropy. Now, assuming we have a pile of cards and we want to shuffle this pile of cards. When the card is being shuffled, what do you think happens to the entropy? The entropy must increase because entropy is the degree of disorderliness. So S begins to change at constant temperature. We call this change Q. So Q gives us temperature delta S. And let's call it equation 1. Recall also that when the card is being shuffled, it is not only entropy that changes, enthalpy also changes. This enthalpy change is gotten from the first law of thermodynamics, which states that enthalpy change is equal to change in internal energy plus the work of pressure which is used to create space. Let's call this equation 2. Now think of subtracting the value Q from delta H. You know, two of them are types of energies for the system. If you subtract Q from enthalpy, what you get is the balance between energy and disorder. This balance reflects the direction of spontaneous process, and it is called Gibbs free energy, whose value is delta G, which is equal to delta H, change in enthalpy, minus T delta S. Let's call this equation 3. So this balance between energy and disorder is the energy available for work, and it is called Gibbs free energy. That is why it is represented with G. Now, if T delta S, whose value is determined by the magnitude of delta S, is so large, then because there is a minus sign between delta H and T delta S in the Gibbs free energy equation, because of this negative sign, it means that the delta G will be negative. And negative delta G suggests a spontaneous process, a self-driven process like dissolution of salt in water. You know, you don't have to force the salt to dissolve because the process is spontaneous and because T delta S is so large. But when T delta S is small, this makes delta G positive. The process is not spontaneous, meaning that energy is needed to perform work. A work like pushing a ball uphill, you need to put in energy for this work to be done. This is also just like trying to shuffle a pile of cards and it refuses to shuffle. What do? Since the use of hands does not work, you use a greater energy source to try to shatter or shuffle the pile of cards. By doing so, you are putting in energy, and it shows that T delta S is too small for the card to be shuffled spontaneously, and this makes the delta G to remain positive. The above statement now leads us to the second law of thermodynamics, which states that the total entropy of an isolated system always increases over time. And the equation for second law is given below. Total entropy change of an isolated system, which of course means the sum of entropy change of the system and that of the surrounding, is greater or equal to 0, confirming the statement that total entropy always increases over time for isolated system.